Welcome back, ladies and gentlemen. Welcome to your Chapter 31 lecture. This one is almost entirely theoretical and historical, so get comfortable because it's story time. We understand by now that light has wave-like properties, hence phenomena like interference and dispersion are possible. But there seems to be an incongruency between light waves and mechanical waves. Waves like waves in the water, what we call mechanical waves, like those in a slinky or what have you, have more energy if the wave is taller or has a higher amplitude. But electromagnetic waves have more energy if they have a higher frequency. Funny, right? How can this possibly be? Well, around the turn of the 20th century, at around 1900 or so, a new theory of physics began to emerge, this thing that we now call quantum mechanics. Quantum mechanics is actually really complicated, and it's so complex, in fact, that there are several different interpretations of what it actually means. But the results of quantum mechanics are quite powerful, so powerful that our entire understanding of chemistry, for example, is built upon it. But what is quantum mechanics exactly? Well, one of the classic examples of quantum mechanics is the famous thought experiment Schrodinger's cat. Imagine, if you will, a cat in a box. Also in the box is a vial of poison that will eventually break open and kill the cat. But I am a cat person, and I really don't like that, so let's refrain from killing any theoretical cats today, shall we? Let's say instead of a vial of poison, there's an automatic can opener and a can of fish. And the can opener is set to go off after an unknown amount of time. Now, if the box is closed, we have no way of knowing what's going on inside the box. The cat could be hungry, the cat could be full, the cat could be eating, the cat could have discovered the fish is rotten, decided not to eat it, all of which are different quantum states, different possibilities for reality to exude, right? For the universe to actually be in. Let's say we have some relative idea of which states are most likely. So we have some vague idea of when the timer is going to go off and open the can of fish. Then we might have some idea of which quantum states are most likely, right? Now, if we add up all of the possibilities of each quantum state, right, the cat hungry, the cat full, whatever, we add all of the possibilities up, they have to add up to 100%. We call the function that adds all of these possibilities together a wave function. That's the probability of all states that the cat could be in. Now, if we open the box, we know what state the cat is in. Thus, reality collapses to whatever state the cat is actually in. And what this means is the subject of several different interpretations of quantum mechanics, most notably the Copenhagen interpretation of quantum mechanics, and so we're not going to go there. Suffice to say, however, that the cat can only be in whatever states are possible, and each state has a certain probability, a certain likelihood of being, right? Now, if we apply the same sort of logic and reasoning to, say, an electron in an atom, we can start to see how it is that an electron might act or react in different conditions. This brings us back to Max Planck and the quantum theory of light around 1900. Planck was able to show that any physical system has discrete energy values, and the values between these are not possible. The minimum difference between these values is very small, and so the energy values seem like a continuum, even though they're not. They're actually quantized and discrete values. Planck was also able to accurately describe the excitation and de-excitation of electrons due to photons, and also giving off photons, between these quantized energy states inside an atom, say the hydrogen atom, for example. He was able to show that the energy of a photon depends also on its frequency. That's our E equals hf. Thus, the constant h, Planck's constant, was recognized as a fundamental constant in nature, and that's why we call it Planck's constant. As a result, Max Planck was able to get the Nobel Prize in Physics in 1918, the same year that we had that crazy flu epidemic. In any case, that Nobel Prize award was for the quantum theory of light. Now, back to electromagnetic waves and energy. Einstein wrote a paper on this thing we call the photoelectric effect. By the way, there is a video talking just a little bit about the photoelectric effect with some probably better visuals and maybe put a little simpler than how I'm going to do it here. In any case, back when he was a Swiss patent clerk, Einstein realized that if you shine light on a piece of metal, I'm going to move the camera here. So let's say my apologies, I had to readjust the lens there for focus. So let's say you've got a piece of metal, right? Maybe you have a chunk of metal here like a bar, and you shine some light on it, right? Now what Einstein realized is that if you shine a light on some metal, some of the electrons are going to absorb the energy from the light and they can be excited out of the metal. However, when he built this into like a circuit, right, some wires, you have like a resistor, maybe, you have a capacitor, blah, 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 something so you can measure the voltage in the circuit, he found something really interesting, very striking. Stronger, more intense light with a greater amplitude, right, like a really, really bright light compared to like a candle, didn't make the electrons that left any more energetic. Instead, what it did is it made more electrons move through the circuit. So it would increase the current, but not the voltage, if you get me. However, when he's shown a bluer light with a shorter wavelength, that increased the energy in the electrons that were excited to move out of the metal. And so by shining a light with a shorter wavelength, he was able to increase the voltage or the electric potential in the circuit that this piece of metal was attached to. What did this mean? Well, obviously the electrons had more kinetic energy, and that meant that the higher frequency light had more energy in it. But also, light stimulated photosensitive material would require a greater voltage to, if you applied a backward voltage here, you would have to apply a greater voltage to stop the electrons from flowing. And that's why, for historical purposes, we call this the stopping potential. In any case, Einstein's original photoelectric experiments generated varying currents depending on the amplitudes of the exposing light and varying voltages depending on the frequencies of the exposing light. Different metals required a different amount of minimum kinetic energy for the electrons to be excited enough to leave the metal. Like I think it took more energy to get the electrons out of lead than it did out of iron. And so the different metals, the different materials have a different what we call work function, or a minimum amount of kinetic energy that you need to excite past in order to get a current to move around the loop. When they applied a voltage to the metal in the opposite direction, of course, it stopped it, calling it the stopping potential. And he quickly realized that the stopping potential was directly proportional to the frequency of the light, because if you remember, that's equal to the energy in the photon itself. As a result, not only did he win the Nobel Prize for Physics in 1921, but we're also determined the charge on a single electron as a result of this this school of thought here, this thing they call the photoelectric effect. Now, they didn't have a really accurate number for h back then, and so it wasn't for a few years that we were able to get really close to the actual value of what we call the elementary charge, or the charge on an electron. But a guy named Robert Millikan didn't believe Einstein, and he spent about 10 years trying to disprove this thing, the photoelectric effect, and trying to prove that photons didn't exist. However, as a result of him trying to disprove the photoelectric effect, Robert Millikan was able to suspend charged drops of oil in an electric field. Now imagine, if you will, you have two parallel plates, right? This one's like negatively charged, and this one's like positively charged, right? And you have a tiny little hole here, and you spray some tiny little droplets of oil here, each of which contains, if they're really, really microscopic and really tiny, a number of electrons that basically you can count. And you have, you know, like a variable battery or something hooked up to this, right? So you can change the amount of voltage on these plates in between whatever values that you need. And if you can have just the right amount of electric field in here, you can get one of these electrons to hover, essentially. Now, if you remember, the electric field times the charge is the electric force. And so if you know the amount of force you have to put on one of these charges, and you know the mass of the oil droplet, you can compare the amount of force that you have to put on the droplet to the amount of charge in it, and figure out what the electron charge is. And that is how Einstein was able to figure out what the electron charge is, sort of on accident. Even though Robert Millikan kind of did a lot of the heavy lifting there. And so Einstein also got the Nobel Prize in 1923 for that. Now, let us revisit this fancy double slit experiment where we had light go through a single slit and a double slit. If light goes through one slit, we see one interference pattern. If it goes through two slits, we see a different one. How's it the photons know that it's one slit closed or not? Well, they don't, right? Photons act like waves, and when they're traveling, as such, they can interfere. Sure, they act like particles when they interact with matter, like exciting electrons and such, but they also act like waves. Hence, we know that light and photons are basically a particle-wave duality. And that's why we say it that way. Now, in 1924, a sort of party boy physics grad student who was being pressured into finishing his doctoral dissertation decided he was going to write a 2-page piece of paper saying that if light behaved like a particle, then matter should behave like a wave. And no one could disprove it. It went from person to person, then institution to institution, and finally, all the way up the chain to Albert Einstein himself. And when Einstein read it, he said that he thought it was great, and it had to be a fundamental consequence of this quantum theory. And so Louis de Broglie, the grad student, was begrudgingly awarded his doctorate, which eventually led him to getting a Nobel Prize. However, it wasn't until some time later that we really understood the meaning of his work. Now, this would be a good time for you to pause and look at the de Broglie wavelength video that I've posted in the chapter 23 lecture page. But suffice to say that if matter moves like a wave, then the length of a wave depends on both Planck's constant, but also the momentum of the particle in question, leading us to this funny thing we call the de Broglie wavelength. So let's take one wavelength, right? And let's apply this one wavelength to the circular orbit of an electron around the nucleus of an atom in the ground state. So it's going to go above, and then about halfway it'll go back to zero, and then below, and then it'll end the wave, right? So above, and then back to zero, and below. Wait a minute, that's a circle, right? Indeed, the allowed quantum state here has to be one where, just like a standing wave, the electron can come back into its own orbit again. Okay, well, that means that 1.5 waves is out, right? Because then it's going to go down here where it should be going up. So you would need, instead, 2 full wavelengths, right? What does that look like? Well, let's make one out a little further, so it's going to go up, down, whoops, and then up, and then down, and then up again, right? I'm sorry, I drew that terribly. So, 1, 2, right? 1, 2. Now, here's our energy state, so it's going to go above, below, and then above and below, right? And so it kind of looks like a beam. 3, of course, if you have 3 wavelengths, it's going to be more like a triangle kind of looking thing. And these states are only allowed because it allows the electron to stay in a stable orbit around the nucleus of the atom. Anyway, we call this the de Broglie wavelength. But trying to track an electron is actually really no simple matter. For one, we don't even know how big an electron is. We only know its charge. And we know its mass. So we've come to realize that it's like smaller than this, smaller than this, smaller than this. We don't know how big it actually is. We know that an electron appears to be everywhere, at all times in its orbital, all at once, leading some to believe that it wormholes through space and time to kind of be everywhere. That has led some physicists to this goofy joke that there's only one electron, and it's everywhere in not only its own orbital, but in every other orbital, in every other atom, everywhere, in all parts of the universe. And so the joke is God is the electron. But in any case, any way you look at it, they move really fast, and they're hard to measure. And the only way that we can really track the movement of an electron are by the photons that it interacts with. However, that comes with limitations, right? Let's say, for example, you wanted to measure the temperature of some hot coffee. You can just look at it and see steam rising from it to know that it's hot, but that's not the same as measuring its temperature. And if you stick a thermometer into the coffee, the thermometer will warm up and the coffee will cool down. And so you're effectively going to change the outcome by measuring it. And the same is true for an electron, because you can measure either where the electron is or how fast it's moving. But the closer you measure one, the less precisely you know the other, right? Because you can measure, let's say you have an electron here, right, and it gives off a photon. This is what you measure, not the electron itself, right? And so you can either know the distance or how fast the electron is moving, right, from the momentum interaction, but you can't know them both. So it is possible that you can know something about the momentum of the particle, the electron, or you can know the position of the particle. But the more precisely you know one, the less accurately you know the other. This is called the Heisenberg uncertainty principle. It's actually B-E-R-G. C-E-R-T-A-I-N-T-Y. Heisenberg uncertainty principle. And that leads me to a joke. And that's how we're going to end this chapter. So, there are 2 physicists. And they are in the car together, out for a drive. One of them is Erwin Schrödinger, and the other one is Heisenberg. Heisenberg is driving, and Schrödinger has his cat in a box in the trunk. So, they're driving, and a cop pulls them over. And the cop asks Heisenberg, because he's driving, "Do you know how fast you were going?" And Heisenberg says, "No, but I know where I am." The cop is not amused. And so he says, "I'm sorry, gentlemen, I'm going to have to search your car." Because obviously he thinks they're loony, right? So he goes and looks in the trunk, and in the trunk he sees a box. And he opens the box, and in there is a cat. And the cat has very clearly gorged itself on a big can of fish. And so the police officer says, "Hey, do you guys know you got a stuffed cat sitting back here?" And Schrodinger pipes up from the front seat, "Well, we do now."